Instead of trying to have the audience see the slides which are flickering, maybe I'll just do a quick overview of CXL verbally, and then we can do a question and answer session. So if any people, we can make it a conversation. We can make it more interactive that way. Um, that's probably the best we can do with the technology acting up this morning. So while you're figuring this out, so CXL 3.0 is a pretty major step function. It's a new specification version that we just released very recently, as recently as September this year, August this year. So CXL 3.0 doubles the data transfer rate over CXL 2.0 because it adopts PCIe Gen 6 electricals. And with the doubled data rate, which is at 64 gigatransfers per second using PAM4 technology, CXL doubles the throughput, right? Without any added latency over CXL 1.0 or 2.0. And to actually get there, when you double the throughput and you don't add latency, so CXL had to do some pretty cool tricks to get there. And there were some pictures in my deck showing exactly how CXL achieved that. And with this increased data rate, CXL increased the flit size from the 64 bytes that we used to have in CXL 1.0 and 2.0. And what that increased flit size did was it gave CXL the ability to pack in some more information on the physical layer during the transfers. And that extra piece of information allowed CXL to scale to brand new usage models. And the usage models is the thing that allows for the increased scalability, increased fungibility, and the fabric usages that I was hoping to show you guys in some pictures about. But at a high level, with CXL 1.0 and 2.0, we were kind of limited to certain topologies, mostly what we think of as hierarchical or tree-based topologies, similar to what PCIe has. With CXL 3.0, in addition to maintaining backward compatibility by supporting all the erstwhile topologies, we also have support for brand new fabric-based topologies, right? Which are peer-to-peer, which are non-tree based, and are extremely scalable because CXL introduced a brand new way of routing information on a fabric using something called port-based routing. So that's one pretty big change in CXL 3.0 over 2.0 and 1.0. Other changes that came about as a result of packing extra information were things like memory sharing. With CXL 2.0, we already had the concept of memory pooling. And memory pooling, as some of you may be aware, allows for memory to be more fungibly provisioned across multiple hosts, right? But the limitation of memory pooling, or the model, not necessarily a limitation, is that a single piece of memory can only be assigned to one host at any given time. It cannot be assigned to more than one. Memory sharing, which is brand new in CXL 3.0, says that now your memory can be shared among multiple hosts, and you can have hardware-based or software-based coherency that can be maintained for the single piece of memory that can be assigned to multiple hosts at the same time. And then apart from that, we fixed a number of limitations that we used to have in CXL 2.0 and 1.0 in terms of the number of switches that can be supported, some of the topology restrictions that existed with 1.0 and 2.0. All of those limitations were overcome. So the way I think about it is that this spec is, with CXL 3.0, we have achieved now a level of maturity with a specification that gives us enough tools in our toolkit to be able to build composable systems of multiple different kinds. We now have a level of spec maturity to be able to scale to usages not just within the node, but even across nodes. I want to pause here because I don't have many pictures to share, and I know my voice will get tedious after a while. So if there are any questions, I'd love to be able to answer some of them or just start a conversation over here.
So Ishwar, this is OCP, Open Compute Project. The audience is very eager to build technologies into systems. So do they need to do everything all over again? Could they benefit from some of the technology they already know?
Thanks, Himak. So the good part about some of the CXL specification and the way it was conceived and way it has developed is that it leverages PCI infrastructure for its electrical and physical layers, right? And it is and because it leverages the PCI electrical and physical layers, we can share a number of the infrastructure components that we have already developed for PCI Gen 5, Gen 6, etc., including cables, retimers, chem slots, what have you, right? All of the PCI infrastructure, the slots, the connectors, all of that can be reused almost as is for CXL. We don't have to invent brand new things. Where new technology and new innovation, I think, is probably going to be needed is to be able to construct systems while being very cognizant that CXL, because it carries coherent traffic, right? We need to be very cognizant about latency. So in the past, a lot of the focus in constructing PCI-based systems has been on other virtues such as getting full throughput or having the system be more scalable or manageable or things like that. In addition to those things, now we have to be also very cognizant about trying to be low latency. So for example, low latency retimers, we need to be able to get to distances across different nodes without, well, preferably without retimers at all, right? So those are parts of system design that CXL introduces over and above PCI.
How about software, firmware, discovery? Are those any different? Do software guys, firmware guys, security guys need to worry about CXL or?
So CXL devices, there are multiple layers of the software stack, right? Starting, let's say, BIOS, right? BIOS discovers CXL devices very similar to how BIOS discovers PCI devices. Now, a traditional BIOS which has no awareness of CXL obviously will not be able to discover CXL devices because it doesn't know where the register locations are defined and things like that. But the BIOS discovery of the CXL topology is very similar to PCI topology discovery and enumeration. Then you have the device drivers, and again, PCI bus driver can be easily extended to make a CXL bus driver. And that is exactly what we are doing in the Linux community as well as for Windows-based bus drivers. And then finally, you have the device drivers. And for the device drivers, just like with PCIe, we have class drivers for different kinds of standard PCI devices such as NVMe. CXL has defined a number of what I think of as instruction sets, which allows people to develop class drivers for different types of CXL devices, and in particular, type 3 devices, such that once you write a CXL class type 3 driver, because of standardization of the register set, you should be able to take the same driver and make it interoperable among different vendors producing the same type of CXL type 3 devices.
Hi. My question is on shared memory. Does the spec define any, you mentioned hardware or software, but the spec define any methods of managing the coherency when multiple hosts are sharing the memory?
So what the spec allows us, what the spec allows us to do, it gives us the semantics and the transport protocol for carrying coherency management messages. What the spec does not do is it does not prescribe how a particular device should maintain coherency across multiple nodes. The spec lists certain examples of how those traditional techniques of coherency maintenance, such as on-die snoop filter or in-memory directory and things of that nature. But it does not prescribe that a device must do it in a particular way.
So one enhancement back invalidate.
Yeah. Siamak was pointing out was one of the protocol messages that I was referring to is the back invalidate message, right? And the back invalidate message, think of that as a snoop type, right? And the device can use that to send snoops to hosts for regions of memory, so as to be able to invalidate the host's caches for that cache line.
That's an enhancement.
Yeah, that's a 3.0 specific thing.
So I've been watching CXL for a few months. That's about how long it's existed. And I'm pretty excited to.
No, I'm sorry. CXL specification was introduced in 2-3 years ago.
Good.
So, and we don't really have to wait for 3.0 to be complete before people can build devices. On the floor, there are devices that are running memory cycles on CXL.
Exactly my point. What's the state of implementation? Is there enough componentry out there where somebody can put together, perhaps not an OCP, experimental setup, but an experimental setup to start experimenting with CXL and working out capabilities and ideas? And if so, it would be very much appreciated if OCP could publish a list or CXL could publish a list of where you can go get the pieces and parts necessary to build an experimental setup. Thank you.
So I'll, answer based upon what I've seen in the expo hall, as of yesterday. If you walk the expo hall, you're going to see a number of different CXL implementations from a number of different vendors. What I saw yesterday when I was walking through that was I saw memory vendors who have taken CXL ASIC using Type 3 devices and created modules of different form factors that they've been showing in their booths. I've seen FPGA implementations of CXL memory for use for memory expansion, as well as for near memory computation and in-memory computation. And you're going to see, and if you walk around, you see CPU vendors advertising CXL capabilities on the CPUs that you see in the expo hall. So I think the last one I remember was a switch implementation with CXL with 256 lanes of CXL. So that pretty much rounds up, you have CPUs with CXL being advertised in the hall. You have device vendors of different types, memory vendors, FPGA vendors, CXL memory for expansion, as well as CXL memory for near memory processing, and switch vendors. So from an ecosystem point of view, I think there is significant traction in actual implementation that we can actually go see and touch like right now. So that is the best boat right there.
CXL specification has a major chapter called compliance chapter. And there's a good set of people working on defining what the compliance is, and work has started to run individual components through the compliance test. Contributors to CXL specifications and members of the CXL Consortium can bring in their solutions and go through an equivalent of a plug fest, run their systems across the compliance test, and get a report on what passed, what not passed. So the members of CXL Consortium can see that report if you like.
Thank you, I appreciate that. I would just like to know that the CXL specs make the Type 3 device like memory agnostic, like we could use any emerging memory and we do not need to change. I mean, it is transparent to the host how we handle it that. And then the second thing is that as Dr. Sharma had said of Intel that the Type 2 advantage is that the complexity is in the host, or at least to implement the cache coherency. So could you explain that more, that the device need not implement? So we have the ARB-MUX, so on the host side, the cache.
This is a very good question, especially a good question for Ishwar. Ishwar is one of the original architects and developers of CXL specification.
So for the first part is CXL Type 3 media agnostic? And the answer is yes. In fact, the whole CXL specification, especially the CXL MEM specification, was defined in a way such that it was transactional in nature in terms of the opcodes that it sends. It's completely media agnostic, right? It doesn't matter whether it's DRAM media or NAND flash media or phase change media or what have you. But the CXL specification also allows for the device to advertise enough characteristics about the media type that is being plugged in, such that the host can manage that media appropriately. Obviously, if you plug in a DRAM type media, your performance characteristics, your power characteristics, your endurance characteristics are going to be very, very different from, let's say, when you plug in NAND flash and try to use that as byte addressable memory. And the host needs to know that, right? You need to know that from a software perspective. You need to know that from a manageability perspective. And CXL allows you to advertise all of that to the host so that the host can manage that media type appropriately. So that's the first one. The second part is the question, I think, was when you have type 2 memory, why is there so much complexity on the host to manage the coherency? So I'll answer this question in the context of CXL 3.0. With CXL 3.0, with the new addition of the back-end validate flow that I was referring to earlier, at this point, the coherency management is much, in my opinion, much more streamlined between the host and the device, because it's now more of a peer coherency model, similar to how we traditionally do SMP or symmetric multiprocessing, where the two cache domains are peers of each other, where each cache domain can maintain independent snoop filtering for the memory attached to that particular host. So is it actually working?
It's working. Actually, since we're on the type, maybe please cover type 1, type 2, type 3.
Okay.
Because this is an audience that might have not heard what CXL is.
Oh, but it's not working. No.
Advancing slides don't show up. We're advancing slides, but they don't show up on the screen. Anyway, what is a type 1, type 2, type 3 device? Ishwar?
CXL has 3 bins of device types based upon usage models. Type 1 and type 2 devices are accelerators. Type 3 devices are memory buffers. The difference between type 1 and type 2 is that type 2 devices have memory attached to it. Type 1 devices don't have memory attached to it. And type 3, which is the most common, prevalent, most the one which has the most traction right now are the ones which are pure memory. They're not accelerators, and they're pure memory for the purposes of memory expansions in terms of capacity expansion, or for emergent memory attach. Any other questions? Go ahead.
We've heard enough about the type 3 use cases. What are you seeing in the industry for type 2?
So the type 2 uptake has been slower than the type 3 uptake. And in what I've seen right now with CXL 3.0, there is now an increased enthusiasm and motivation for type 2 adoption. And that comes from the simplifications that CXL 3.0 brings to the coherency protocol. Primarily, what I've seen so far, I can't really talk about specific companies and products which are unannounced products right now, is in the GPU space is the place, and the FPGA place are the 2 places where type 2 was actually aimed at when it was first conceived. And those are actually the 2 places which I have seen the most traction and interest in development. So I do expect, as we get further in the CXL 3.0 time frame, we're going to see more type 2s. But they're not going to be as many vendors, I don't think, as we have for CXL type 3, which I think is much more of a mass adoption kind of a product. Go ahead. Yes, please.
Hi. So one question about coherent attach. So historically, and you mentioned FPGA products, like historically, close coherently attached accelerator systems like FPGA we were doing co-packaged FPGA plus Xeon processors, things like that, we typically saw degradation in the coherence performance because typically these accelerators run at slower clock speeds than the core complex. And typically this has a knock-on impact to energy management and so on. And so in general, these systems have not become very prevalent for these reasons. Do you have use cases and designs in mind that avoid those traditional problems with this setup?
So this is a very good question. It's very, I have seen firsthand the co-packaged FPGA CPU products with some of the limitations that I think that you were talking about. The limitations come from two sources, in my opinion. One is how coherency is maintained, right, across these two processing elements. Some CPU vendors, use in-memory snoop filters, and that itself is the cause for spurious snoops and also for the cause of the slowdown, because the second element, which is the FPGA, processes these snoops at a slower clock rate, right? And that leads to a slowdown. In my opinion, those things are implementation limitations rather than specification limitations. Today, what we're talking about are really just specifications, right? One can implement things in a more optimal way than some of the implementations that you may have seen. But it's not really a specification limitation. And those things are using proprietary, I would say CPU vendor proprietary protocols, not necessarily industry standard protocols like CXL. Anytime you have FPGAs which are doing high bandwidth snoop processing, I think we're going to end up in the same kind of limitations that you talked about. Hopefully, implementations will do a better job of snoop filtering so as to limit the number of snoops that actually have to be sent down to these FPGAs. I think that's the only answer there.
Thanks. I just would say I think that there's more work to be done in the specification side in terms of how to navigate around these challenges, because as you said, it's about how you implement the coherence, but the coherence itself is a protocol, and this is a protocol riding on top of the protocol. So I think that there's still work to be done in how we navigate around those types of challenges to make this use case work. Thank you.
Thank you. Are we done? Yeah. All right. Thank you so much.